This is a continuation of the lecture on closed sets. This is sixth lecture in the series on metric spaces. Hopefully, this should be short because there is one case. Do you remember? We have a short list of metric spaces, and our policy is that to illustrate, explain all the concepts for these examples. So there is one example which I couldn't do it in the last time because of time constraint. So I plan to do that. And I also, if you remember, towards the end, I introduced the notion of a limit point. We will quickly go through it and characterize closed sets with respect to limit points. That's the aim of this lecture. So let us get started. Yeah. So the example which we forgot is the following. Okay. XD suppose is a metric space and A is a non-empty subset. Let me call it Y. Y is a non-empty subset of X. Then we can restrict Y to get a metric. This is a metric space. All right. So what we want to do is suppose let us recall. We have seen that if V is a closed open set in the metric space YD, if and only if there exists an open set U in XD, this metric open set in the metric space XD, so that V equal to U intersection Y. This we are already known. This is a fact we have seen. Okay. Now we want to look at the case of closed sets. Okay. Right. So let B in Y be closed in the metric space YD. Right. Okay. What does this mean? This means that Y minus B, this is a subset of Y, is open. Where? In the metric space YD. You understand that? Everything is happening only in the space YD. So if you want, this is a picture of X, this is your Y, and this may be your A. Sorry, what is it? B. Yeah. You follow that? Okay. Now let's look at, call this as Y minus B as V. Okay. And V is open in YD. Therefore, by this result, I know there is an open set U contained in the metric space XD such that V is U intersection Y. Would you accept it? I'm just using this fact. Okay. It will be nice to have some kind of a picture. I may or may not be able to do that. Y minus B is this one. Yeah, maybe some other color maybe look better. So this is Y minus B, the pink color or whatever, right? So what do I know? There is an open set U. Okay, this may be an open set. Let us look at the open set in some other color. Okay. This may be the open set. Okay, when intersected with Y, it happens. Something like this. Okay, don't look at the picture too much because I'm drawing just like that. I'm not very good at, and I'm not even paying very careful attention whether it's absolutely correct or not. Okay, just to have some kind of an idea what is happening. Okay, don't I? All right. Okay. Now the what I would like to say, therefore, you can the picture says if I look at x minus u, what do I know? This is closed. Okay, this is your u, the green one. Okay, this is your u. Okay, right. So this is closed, right? In where? In the space xd. Right. Now the picture shows, or call it if you want, A. Right. This A is closed. The picture shows A intersection Y may be B. Okay, suppose it's true. What do I have proved? We have proved the analogous of this fact. Any open set in YD is got by intersecting an open set in X with Y. And similarly, any closed set in Y is got by intersecting a closed set in X with Y. Do you understand this? Very good. Now, how do you prove that? That's where I hope it's easy. You just have to set theory. I have to keep very careful bookkeeping. Suppose X belong to A intersection Y. What does it mean? X belong to A and X belong to Y. Okay, what does X belong to A mean? This means if and only if X belong to X minus U and X belong to Y, right? If X, you follow that, if X belong to A means X belong to U. This means this is if and only if X is not in U, but X is in Y, right? Okay, so what does it say? I want to say it is in B. Okay, right? I want to know whether it is in B. Let us directly prove it. So let X belong to A minus B. Question is whether X is in B. Suppose X is not in B, right? Remember, X is already in Y, right? Therefore, X is in Y minus B, which is B complement, but that is our B. Therefore, X is in V. You understood that? Yeah. If X is in V, okay, what is V? Yeah, X is in V. Now I know X is U, sorry, oh, X is in V. V is U intersection Y. Therefore, X is in U. Yeah. But what is X is in U? If X is in U, X is not in A. Right? If X is in U, but that's a contradiction because I started with X is in A. A is U complement. You understand that? So these two things contradict. Therefore, what I have shown, if X belong to A intersection Y implies X belong to B. Just to go through it quickly, I suppose X belong, I want to say X belong to B. Suppose X is not in B, that means, remember X is already in Y. Therefore, X is in Y, but not in B. But Y minus B is what? Y minus B is our B, right? Therefore, X is in B. But what do I know about B? B is U intersection Y. Therefore, X belong to B, which is U intersection Y. In particular, it says X is in U. But what is A? A is U complement. Yeah, that's a contradiction. Yeah, contradiction. So what does it prove? This is proved. And let us look at converse is similar. Suppose this X is in B, I want to know whether X is in A intersection Y. That is whether X is in A and X is in Y. X is in B, but B is a subset of Y, therefore X is in Y. Y. That's clear. Therefore, I only have to say the crucial question is whether X is in A. Again, let us do the same thing. Suppose X is not in A. You see that these are all set there. You just have to keep a clear head. Okay, sometime, okay, in the board I may be able to explain, but in this pen on paper, sometime I may get confused. Or it could happen other way around also, right? So nothing to worry. Suppose X is not in A. Let us look at the thing. If it's not in A, then what is it? It is in U. You understand that? If X is not in A, then X is in U. Okay. You understand this? X is not in A, that is X is in U. If X is in U, remember X is also is in Y. Therefore, X is in U intersection Y. But that is V. Therefore, X belongs to V. But what is B and V? How are they related? V is B complement. That's a contradiction. That is, it is B complement. But I start with X in B, X in complement. This is a contradiction. So, what have you proved? Please go through. So, what have you proved is if B in Y, this is with respect to YD metric. Okay, this is closed. Okay, if only if, okay, or simply say there exists a closed set A in the metric space XD So that B is A intersection Y. Okay. And converse is also true. I leave it as an exercise. Okay. Please do that. Just again, please remember this is just a set theory. There is nothing to worry. If you get confused, if you get lost, don't worry. Take a new page and start working. If you look at the old one, you will still get confused. Okay. It's exactly similar way. Okay. Please do that. So this is over. So we are done in all our examples. We have found out some the facts about closed sets as it was our policy. Very good. Now the next question I want to ask is something a probing question. It's a probing question. What is a probing question? We already asked in the last lecture. What is the probing question? Suppose I have a metric space xg and suppose A is a subset of X, and what is it meant say it's not closed? What does it mean? Remember, when do we say A is closed? If X minus A is open, if and only, right? Therefore, this A is not closed if and only if X minus A is not open. See that we are just simply investigating. We do not know what we are going to arrive at. Even though if you had understood my last lecture, you know what we are going to arrive at. But if you are looking at it or if you didn't understand it properly there, again, this is the chance. This is not open. Now, if this is not open, what does it mean? Remember, U is a set. When do I say it's open? For every, this is open. If for every X in U, there exists an R positive such that BXR is completely contained in U. So if this is false, that means there is at least one X in U for which whatever R you give me, that is for every R you give me, BXR is not contained in U. You understand that? Now, what does it mean BXR is not contained in U? That means there exists a Y in BXR so that BXR is not in U. Otherwise, if you have for every Y in BXR, Y belong to U, then BXR will be a subset of U. You understand? So that's not true. That means there is a Y so that BXR is not in U. You understand? Therefore, this means if and only if, okay, there exists an X where in X minus A, so that for every R positive, okay, BXR, look at that, there is a Y in BXR which is not in U. That means this is if only U, there is a Y in BXR. It's not in U, but what is U? Okay, you understand this? I am just applying to the case where U equal to X minus A, right? It is not open. Suppose this is open, X minus A equal to U, not open. That means there is an X in U, so that is happen. Okay, therefore there is a Y, but not in U. That means there is a Y which is in A. Therefore there is a Y in BXR. Are you following? Please go through it. Therefore there is X in the complement, so that for every R positive, BXR intersection A is not empty. This all this is if and only. Do you understand this? So if you want, formulate as a lemma or some such thing. A subset A in a metric space X is not closed if and only if there exists X not in A, that is in complement, so that for every R positive, right? Okay, BXR intersection A is not empty. Okay, pause, review, proceed. I should actually give pause, review, proceed here. So this point X has something special with respect to A. You see that? What does it say? Okay. This may be my set, this may be my A, and X is here, so that however small open ball I take, it always intersects A. Okay, that's what it says. So this kind of points have some special affinity to A. So, okay, special affinity meaning affection, liking, or a love, or whatever you want to call it. It's a fan. Okay, the X is a fan of A. Some sort of thing. You follow that? Okay. So let us try it and say formulate the definition. Let A be a subset of a metric space. X in X is a limit point, or if you want, limit point with a K silent. K silent. As I wrote earlier, silent as a knife or night or whatever the words you can think of as in. The reason is nowadays the definition of limit point is something else, what I call usually cluster point or accumulation point. Okay, but I will stick to this definition. Okay, I say it's a limit point if for every R positive, okay, BXR intersection A is not empty. You follow that? That is, there is a Y in A, so that Y belong to BXR. I'm just saying the same thing. Okay, this is called a limit point or K limit point. Uh, as I said, K is silent, therefore I should pronounce it only as limit point. So following Americans, I will not, since the K is unnecessary, so I will simply write it as limit point. But what I mean is this point. Okay, just for fun, don't get worried. Okay, so in terms of this, how do I formulate the lemma now? Lemma says if A is not close, okay, there is a point A like this. What does it say? X is not in A is okay, but what is this? For every R positive, BXR intersection A is not empty. That means X must be a limit point of A, but unfortunately X is not in A. Do you understand the lemma now? Please pay attention. These are, we will prove it in a minute again. Okay, we arrived at this lemma, but I will again prove it if and only statement. So what this says is, if A is not close, what does it say is, there exists a X. What kind of X? For every R positive, BXR intersection A is non-empty. What does it say about X? That X is a limit point of A. That therefore, this lemma can be reformulated. How do I reformulate? If A is not closed, if and only if there is a limit point of A which is not in A. Do you understand that? So reformulation of the lemma. I will formulate in a positive way and prove it. Close. If only if there exists a limit point of A which is, does not belong to A, which does not lie in A. That's all. So what will be the positive way of saying A is closed if only every limit point of A belongs to A. Do you understand this? So this, a positive version of this is the formulation. So I will call it a proposition or a theorem. It is exactly the same. Okay, A is closed if and only if every limit point of A lies in A. Okay, you will see that I'm going to give a proof, but the proof is essentially a sham, a cheat. Why? I'm going to repeat the same argument. Okay, but maybe it's better to, because this argument was essentially I wanted to motivate how I arrived at the definition of limit point. Usually nobody kind of motivates how limit points are considered, why it is defined like that. Nobody considers. Whereas here we are asked a nice question, Based on that question, we arrived at the concept of limit point. So that was the main aim of this. As a corollary, we found out the lemma, right? But I am reformulating lemma in a way which will be more useful to us. A is closed if and only every limit point. Therefore, what is if A is not closed? What does it mean? There is a limit point of A which does not lie in A. That's all we proved. That's all we proved. You see that? Anyway, so please try to understand, pause, review, and stress. So don't worry about the proof. If you can to understand this proposition and the lemma, they are one and the same. Try to appreciate. I am going to give an easy proof. What is the importance of this? See, now we have two definitions of closed set in a metric space. What are the first one? A is closed if the complement of A is open. The other one says it's somewhat intrinsic. Every limit point of A lies in A. A is closed if and only if every limit point of A lies in. So these two are characterization. So depending upon the situation, I can use any one of the two definitions to prove a set is closed. Okay, it's a very, very powerful proposition. Okay, especially you are going to be an analysis, even in topology, you will see this is a much better way of proving various things. Anyway, okay. So let us assume what is that? A is closed. What do I have to prove? Let X be a limit point of A. So what is that I have to prove? To prove X belong to A, right? Okay. So let us assume, suppose X is not in A. What does it mean? Now what do I know about A? A is closed. Therefore X belongs to U, which is X minus A. What do I know about U? U is open because A is closed. I am using the definition. You understand that? Now since X belongs to U and U is open, what do I know? This means there is an R positive. With what property? BXR is completely contained in U, right? Now, what do I know about X? X is supposed to be a limit point of A. Therefore, what do I know about BXR? BXR intersection A is not empty. But this is BXR intersection is contained in U, but what is U? U is A complement. That means BXR intersection A is empty. But that's a contradiction because since X is a limit point, this is not empty. So, okay, this contradiction shows X must be in A. Pause, review, proceed. Notice that I'm just essentially repeating the earlier argument. Converse. What is the converse? Let A be such that, okay, if X is a limit point, then X belongs to A. So what do I want to prove? A is closed. Okay. Suppose A is not closed. This is what I want to prove, right? Suppose not. If A is not closed, what does it mean? What do I know about the set U, which is X minus A? This is not open, right? Because if it is open, then A will be closed. Therefore, this is not open, right? Okay. If this is not open, what does it mean? That means there exists a Z. Since I am using X, I am not doing that. There is a Z in U. That is, there is a Z. That is same as saying X is not in A. Z is not in A. There is a Z in U. So that for every R positive, B, ZR is not contained in U. You understand that? If it's not open, there is at least one point so that no open ball can be found around Z, which is completely contained in U. That means you take any open ball, BZR is not contained in U. If it is not contained in U, what does it mean? There exists a Y in BZR so that Y is not in U. If Y is not in U, where is it? What is U? U is a complement. Therefore, Y is in A. So what does this say? For every this says for every R positive, Okay, we have found BZR intersection A is not empty because there is always a Y here. So what does this say about Z? This says Z is a limit point of A. If Z is a limit point of A, by our assumption, remember if X is a limit point of A, X must be in A. Therefore, Z must be in A by hypothesis, right? But where did we take Z? This is not open. That means there exists Z in U. That is, Z is not in A. But we conclude Z is in A. That's a contradiction. Okay. I hope you understood. Pause, review, proceed. So usually textbooks and teachers will define closed sets as complement of open sets, immediately prove the class of closed sets. Namely, empty set is closed, full set is closed, arbitrary intersection of closed sets is closed, finite union of closed sets is closed, and arbitrary union of closed sets need not be closed. The proof is that's it. Okay. But now you can see we have proved all those things and we have looked at lot of examples. And not only that, by asking correct questions, we arrived at a definition, a concept, namely the concept of limit point. And that helped us to characterize closed sets. A set is closed if and only if it contains all its limit point. That's a fantastic result. You just cannot say really value that it's really so good. Okay, let us see as you go along in analysis, topology, or related area wherever these kind of concepts are used, you see that. And please note one thing, please do not be intimidated, okay, by other people. Limit, this is not the point definition of limit point, etc. Right? You just counter them. My limit point is this is a spelling. Okay. I'll pronounce it limit point with ki silent. Okay. Enjoy. We will meet again.